Harsh,
Yeah, hello.
hello. Am I audible?
1 second, sir. Hello.
Yes.
Yes, sir. Good evening.
Good evening.
Good evening, sir.
Do you have any idea or do you have any doubt from first term syllabus? Or should we start with the second term?
Sir, I guess we should start with the second term.
Okay. Do you have any doubt from first term syllabus in calculus part or any other thing?
Maybe a system of particle and rotational motion.
Okay. So let's start with second term syllabus first. Mechanical properties of solids. To start this particular chapter, let me define you some term related to this. You must have learned about spring in chapter number 6, work, energy, and power.
Strength. No, I didn't hear the term strength in school.
I'm asking, you must have learned about spring in
Oh,
chapter
okay,
number
yeah.
6.
Spring, yes,
work,
yes, spring.
Okay. Suppose there is a support from which a spring is attached whose natural length is L. Now, if you compress this particular string or stretch this particular string, so its shape will be like this, or it may deform like this. So on compressing it along this direction, on stretching it along this direction, you must have applied some of deforming force to change the shape of this particular spring from its original state, that is from this point, to compress it a little bit more towards this or stretch it towards this. So this force is called deforming force, which will be responsible to deform the shape of this particular spring. Is it clear?
Yes, sir.
Now, there is tendency of this particular spring to restore back to its original state. So a force will get developed into it along this direction. And in this part, it will be along this direction, which will bring this particular spring back to its original state. This force is called a restoring force. So we mainly have two different forces. First is deforming force, which will be responsible to deform the shape of a particular object. In this case, this deforming force is deforming the length of this particular spring, by which a force will get developed into it, which will tend back this particular spring back to its original state. This is called restoring force. Is it clear?
Yes, sir.
So this spring has a tendency by which this restoring force get developed into it. This tendency of a spring is called elasticity. So we first define what do you mean by elasticity. Similarly, as behavior of this particular spring, solid behaves. Suppose for a particular solid, there will be arrangement of particles like this, in which each corner is occupied by some atom or molecule, let's say like this. And we just assume that the bond in between each particle is spring-like structure. So let's say like this. So if you apply any deforming force to this particular solid in any one direction to deform its shape, let's say along this direction. So this spring has the ability to develop a restoring force into it along this direction, which will be responsible to keep this particular point back to its original state. This tendency of body by which this restoring force get developed into it, which will tend to bring this particular particle back to its original state, is called elasticity. Is it clear?
Yes, sir.
So we first define what do you mean by elasticity. So it is the tendency of body due to which it can regain its original state or original configuration on removal of deforming force. There is another property which is opposite to this particular elasticity, is called plasticity. So you'll say, if a deforming force is applied on a particular object and they have can't ability to regain back to its original state on removal of deforming force, this inability of a particular object is called plasticity. Is it clear?
Yes, sir.
So plasticity is the inability of a body so that they can't regain its original state or original configuration on removal of deforming force. Is it clear till this part?
Yes, sir.
Okay. Now, there is no any object which behaves perfectly elastic or perfectly plastic. So the behavior of body lies in between elasticity and plasticity. But we consider the maximum elastic substance and the maximum plastic behavior of particular substance. So maximum elastic behavior will be of cords and maximum plastic or plasticity will be of wax. So you can say cords are most elastic behavior substance and wax is the least elastic, or you can say most plastic behavior substance. So in general, property of a body lies in between elastic and plastic. So you can say behavior of body lies in between elastic and plastic. Is it clear till this part?
Yes, sir.
Okay, so let's write it down, or we may take a screenshot.
Done, sir.
Okay. Now, on the basis of this deformation and restoring tendency, we may define some term related to this. First is stress. Suppose you have a body which is attached to any fixed support like this. And if you apply any deforming force to it along this direction, this is deforming force which is acting on this particular cross-sectional part. So this is called area of cross-section. So stress is basically the amount of deforming force applied on a body per unit area of cross-section is called stress. So stress is the amount of deforming force applied on a body per unit area of cross section is called stress. So you may say stress equals to deforming force divided by area of cross section. Now, for this particular stress or measurement of this particular stress, we may define its unit as it depends upon two factors. First is force and second is area of cross section. So unit of force is Newton and unit of area of cross section is meter square. So you can say SI unit is Newton per meter square. Is it clear?
Yes, sir.
Okay. Now, on applying this much amount of deforming force to this body, some deformation will get produced into it. Let's say it will be along this direction like this. So this is amount of deformation produced, which is delta L, with respect to actual length of the rod from this point to this point is L. So if you have to calculate amount of deformation produced in this particular substance, it will be defined by another physical quantity, which is called strain. So strain basically defines you amount of deformation produced in a particular substance on applying this much amount of stress to it. So strain is the ratio of deformed shape to the original shape of body. So strain equals to deformed shape divided by original shape of object. As you see, the deformation is delta L, which must be measured in terms of length, or its SI unit will be meter. And original length is also L, which is also measurement of length. So its SI unit will be meter. So both numerator and denominator having same unit. So on taking ratio of these two terms will give you unitless quantity. It means strain is unitless quantity. Is it clear?
Yes, sir.
Okay. Just write it down or may take a screenshot.
Start of the screenshot.
Okay, done?
Yes, sir.
Now, there is a relation between this applied stress to this amount of strain developed into it, which is defined by Hooke's law. So there is limitation of this particular Hooke's law first. First, temperature of this material or system to be constant, and next, it should be within elastic limit. I will define you what do you mean by elastic limit and why temperature should be constant in this part. So Hooke's law says at constant temperature and within elastic limit, the more you apply stress to a particular object, more deformation will produced into it. Means stress and amount of strain developed into it should be directly proportional to each other. Is it clear?
Yes, sir.
So say at constant temperature and within elastic limit, the strain produced in a body is directly proportional to the applied stress. Means stress applied to a particular substance is directly proportional to strain produced or strain developed. So if you replace this proportionality sign, there should be some constant of proportionality. So it will be stress equals to E times strain. This E is constant of proportionality for this part, which is also called modulus of elasticity. Is it clear?
Yes, sir.
Okay. Now you can say as stress is directly proportional to a strain, so the graph in between them will be straight line. So if you draw a graph related to these two terms, this is stress applied and this is corresponding change in strain. So the graph of these two terms will be straight line. Is it clear?
Yes, sir.
So if you rearrange this particular equation, you will get E equals to stress divided by strain. Now, this particular relation is nothing but ratio of perpendicular and base. So you must have learned in graph, perpendicular and base defines you slope of that particular curve, which is defined by tan theta. So you can say this is slope of stress strain graph. Let's say this particular line is inclined at some angle theta. So if you take tan theta, which is slope of this particular line, so it will be equivalent to E. Is it clear?
Yes, sir.
Now, the next term will be, what do you mean by modulus of elasticity, or what would be the physical meaning of modulus of elasticity? So you'll say, modulus of elasticity defines you the elastic behavior of a substance. Greater the value of modulus of elasticity, which means the substance is more elastic. Next, it will depend upon two factors. First is temperature and second is nature of material. Next, it will be independent of dimension of body. It means if we change length, width, radius, or any physical dimension, there will be no impact on elasticity of that particular object. So you can first define what do you mean by modulus of elasticity. So you can say it defines the elastic behavior of a substance greater the value of modulus of elasticity, greater will be elastic nature of substance. Is it clear?
Yes, sir.
Just take a screenshot.
Okay, sir.
Okay. Next is factors affecting modulus of elasticity. So you will say it depends on nature of material and temperature. So you'll be asked how modulus of elasticity will be affected on changing the temperature of substance. So you'll say, if you increase the temperature of a substance, so there will be weakening of the bond in between particle. So if bond get weakened, so particle gets separated from its original point. So if separation between the particle increases, there will be lesser possibility of returning back to its original state. It means it decreases the elastic behavior of substance. So you'll say modulus of elasticity is inversely proportional to temperature. So you may be asked, how will modulus of elasticity will change with change in temperature? So just remember, it will be inversely proportional with change in temperature. Is it clear?
Yes, sir.
And next, it is independent of dimension of body, length, radius, area, and so on. Now, as modulus of elasticity equals to stress divided by strain, and in which strain is unitless quantity, so stress having unit Newton per meter square will be equivalent to modulus of elasticity. So you can say SI unit is Newton per meter square.
Okay, sir.
So we have just defined three different terms related to this formation. First is stress, second is corresponding strain, and third is Hooke's law, which defines you modulus of elasticity. Now, we may define different types on the basis of these different terms. You may take a screenshot to this part.
Okay, sir.
Okay. Now, let me define you types of these terms. So first is longitudinal. Suppose I have taken two different objects. If you apply any deforming force along this direction or any deforming force along this direction, so there will be change in length along this direction in this part and along this direction in this part. So deformation is along this direction. Original length of object is from this point to this point, and deforming force is this. In second part, deforming force is applied to compress it, such that deformation is from this point to this point, let's say delta L, and original length is from this point to this point. So first, in this part, on applying deforming force along its length, there will be possibility of elongation in that particular wire. So it is called tensile. In second part, deforming force is applied to compress it. So it is called compressile. Is it clear?
Yes, sir.
So we may define this longitudinal in two different ways. First is tensile and second one is compressile. So tensile is the amount of stress applied over this particular object to elongate it. Just 1 minute. Harsh? Okay. So first for tensile stress, we'll say if deforming force is applied per unit area to elongate it, that is called tensile stress. And second part, you will say if deforming force is applied
Compression.
per unit area to compress it, that's called compressile stress. In both sense, there will be same formula, that is deforming force per unit area, but there is only change in direction or notion of acting of deforming force. So you'll say first, longitudinal stress equals to force divided by area of cross section. Correspondingly, there is change in length of that particular object. So it should be called as longitudinal strain. So it will be delta L divided by L. And now if you divide these two terms, which will define you modulus of elasticity, and in this part, it is called Young's modulus. So Young's modulus equals to longitudinal stress divided by longitudinal strain. Young's modulus is denoted by Y. Longitudinal stress is force per unit area. Longitudinal strain is delta L divided by L. So on rearranging, you will get Y equals to F into L divided by A into delta L. And this Young's modulus will have same property as we have just defined for modulus of elasticity. Is it clear?
Yes, sir.
Next, since this Young's modulus is defined along its length, so it is also called elasticity in length. elasticity in length for that particular object. Just take a screenshot till this part.
Done, sir.
Do you have any doubt till this part?
No, sir. Not enough.
Okay. Let me give you a question related to this. A wire having length 2 meters, area of cross section 4 mm square, is hanged vertically to rigid support. If a force of 20 kilonewton is applied, find first amount of stress, second amount of strain developed into it. If Young's modulus equals to 2 into 10 to the power 11 Newton per meter square, and third amount of elongation, that is delta L. Let me define you how to approach a problem. First, write all the term which is given in the question. So we have length as 2 meters. Next, area of cross section is 4 mm square. And next, force applied to it is 20 kilonewton. And last, Young's modulus is 2 into 10 to the power 11 Newton per meter square. First, try to check, is there in all quantity is in SI unit or there are in some other unit? Let's say for this particular length, which is in meter, so it is in SI unit.
Yes, sir.
Area of cross section, which is in mm square. So SI unit of area will be meter square.
Meter
So first, you have to convert this particular area into meter square. So do you have any idea how to convert mm square into meter square?
No, sir.
How to convert mm square into meter square? Let me define you. Just 1 minute. You must have learned how to convert the unit from one term to another. Suppose you have 10 to the power 0, which is called base unit. Let's say I'm just calculating for length, so it will be meter. So 10 to the power minus 1, it will be decimeter. 10 to the power minus 2, so it will be centimeter. And 10 to the power minus 3, so it will be millimeter. Is it clear?
Yes, sir.
While taking the area respective to this particular component, it will come meter square, decimeter square, centimeter square, and mm square. So we just multiply those quantity by itself. So while taking area, it will be 10 to the power 0. It will become 10 to the power minus 2. It will become 10 to the power minus 4. And it will become 10 to the power minus 6. So this will be mm square, centimeter square, decimeter square, and meter square. I'm just writing these terms with respect to meter. It means mm, on converting into meter, you must have to multiply by this amount. Is it clear?
Yes, sir.
So you can write area equals to 4. Here we have mm square. So if you have to convert mm into meter square, you must have to multiply it by 10 to the power minus 6. Is it clear?
Yes, sir.
Similarly, if you raise its exponential, let's say 10 to the power plus 1, 10 to the power plus 2, and 10 to the power plus 3. So this is called deca, this is called hecto, and this is called kilo,
Kilo. Yeah.
which means 1 kilo is equals to 10 to the power 3 to its base unit. So we have force in terms of kilonewton. So how to convert it into base unit? So you must have to multiply by 10 to the power 3.
3.
Is it clear?
Yes.
So it will be 20 into 10 to the power 3
3.
Newton.
Yes.
Now we have all the values in SI unit. So just apply the formula, put the values and simplify it. Try to solve. First, write the formula for stress. So stress
Okay, sir.
equals to force by area. Now put the value of force and area of cross section
Yes,
and
sir.
then simplify it.
Okay, sir.
Harsh, any problem while solving?
So I'm getting 5 into 10 raised to minus 3.
You have done a little mistake while how to solve exponential. Let me define you the concept behind it. Stress equals to deforming force by area of cross section. Put the value of force, which is 20 into 10 to the power 3, and area of cross section as 4 into
4
10 to
into
the
10
power.
raised to minus 6
Good.
meters square.
So this 4 and this term will cancel out in 5 times.
Yes.
Now we have 10 to the power minus 6 in denominator. So if you move this term into numerator, its exponential will become positive 6.
Positive. Yes, sir.
So it will be 5 into 10 to the power plus 3 already and 10 to the power plus 6 on bringing this particular term to numerator. Now we have two terms having same base as 10 and
10 raised to power
exponential
9.
as 3. Good. So it will be 5 into 10 to the power 9 Newton per meter square as stress. Is it clear?
Yes, sir.
Now, next is how to calculate a strain. So for strain, you have first delta L divided by L. But in the question or in this given part, there is no any information about delta L. So we
Yes,
can't
sir.
use this formula.
Yes, sir.
So we can use another one. According to Young's modulus, we had stress divided by strain. So for this part, you have the value of Young's modulus and applied stress to it. So on rearranging, you will get strain from it. Is it clear?
Yes, sir.
Try to solve for strain for this part and put this particular value of strain in this first equation to get delta L. Try to solve. Any problem?
Sir, like Young's modulus has a value, right?
Yeah, y equals to this much. You have to take a screenshot of this part.
No, sir, no, sir.
Just take it.
Okay, so done. I took the screenshot.
Now put these values and try to find strain.
So strain value is 2.5 into 10 raised to 20.
Strain equals to stress divided by Young's modulus. We have calculated a stress as 5 into 10 to the power 9.
Yes, sir.
And you have Young's modulus as 2 into 10 to the power plus 11. So if you divide these two terms, 5 divided by 2 will be 2.5. Move this particular term to numerator. So it will be 10 to the power
Oh,
9. And on moving
sorry,
it
sir,
to...
I did some. I actually assumed minus 11. And I gave
Okay.
so it became plus. Sorry, sir.
Okay. So it will be 2.5 into 10 to the power minus 2 only.
Oh, yes, because it was, I took in minus 11, the denominator, and took it up there, it became plus.
Okay, okay. Now put this value in this part to get delta L.
Okay, sir.
So delta L will be L times strain. As you have length of wire 2 meter and strain we have calculated as 2.5 into 10 to the power minus 2.
5 into 10 raised to minus 2.
So it will be 5 into 10 to the power minus 2 meter. So
Meter.
if you convert into centimeter, it will be just 5 centimeter.
Okay.
So you have any doubt till this part?
No, sir.
Okay. So this is the first type of stress strain. Next is related to shape, which is called tangential or shear. Suppose you have a cylindrical body like this. Whose base is fixed. Now, if you apply deforming force on it tangentially to its top surface, so it may get shifted a little bit like this. So deformation in this wire will be from this point to this point along this direction. So in this part, I've just applied a tangential force along this direction, that is F tangential. Over this particular cross-sectional area, due to which there is shift from this point to this point, let's say X. Length of wire or length of this particular cylindrical rod is L, and there is deformation in its shape like theta. So first we define related to this part, that is stress. So it will be called as shear stress. So amount of deforming force, and it should be tangential to it. So it will be F tangential divided by area of cross section. Is it clear?
Yes, sir.
Correspondingly, there is change in shape, which is called shear strain. So it will be equals to theta, which is equals to X by L. You must have learned for small angle, sine theta equivalent to tan theta, and which will be equivalent to just theta. So if you define tan theta for this particular part, tan theta will be equals to perpendicular by base. That's why it is equals to X by L. Is it clear?
Yes, sir.
Now, if take the ratio of these two terms, which is called modulus of elasticity. So in this part, it is called shear modulus. So it will be equal to shear stress divided by shear strain. Shear modulus is denoted by G, or in some other book, it will be denoted by Greek alphabet eta. So it will be equals to shear stress, that is F tangential acting over area, divided by shear strain theta, which will be equal to F tangential into length divided by A into X. Now, in this part, on applying this tangential force to it, there is change in shape of this particular object. So you can say this shear modulus will define you elasticity in shape of this particular object. Is it clear?
Yes, sir.
Okay. Just take a screenshot.
Done.
Let me give you a question related to this. Suppose you have a cube of side 10 centimeter whose base is fixed. Now, a force of 40 kilonewton is applied tangentially to its top. Find first shear stress, shear strain if G is 4 in 10 to the power plus 8 Newton per meter squared. Just use the formula and try to simplify. This is your question. There is a cube on which a force of this much amount is acting tangentially to it. So first you have to calculate a stress. So for a stress, you just need two terms, amount of deforming force or tangential forces. So it is
F into T by,
it will be 40 into 10 to the power 3 Newton. How you will calculate area of this particular surface? You must have remembered the face of a cube behaves as a square. So the area of a square will be side into side.
side into side.
So area will be side into side. Side is 10 centimeter. So divided by 100. 10 centimeter divided by 100. So this 0 and this 0 will cancel out. So you will get 10 to the power minus 2 meters
Minus
square.
2 meters square.
Now just put the formula.
F into T by so 40 into 10 raised to 5.
Good. So force divided by area of cross section. So you will write 40 into 10 to the power 5, or you may write 4 into 10 to the power 6 Newton per meter square. Similarly, G equals to stress divided by strain. So shear strain will be equals to shear stress divided by G. We have shear stress as 4 into 10 to the power 6,
Yes, sir.
and value of capital J is 4 into 10 to the power 8. So 4 and 4 will cancel out. So you'll get 10 to the power minus 2.
Minus 2.
Okay.
Yes, sir.
Do you have any doubt till this part?
No, sir, it's clear.
Good. You may take a screenshot till this part.
Yes, sir. Done, sir.
Okay. So is everything clear from
Yes, sir.
today's class?
Yes, sir.
Okay. So let's stop here for this part. In
Okay.
next class, I will define you bulk modulus or volumetric. And there is one definition or one derivation in this particular chapter, that is potential energy stored in wire, and one last part, stress strain curve. Okay.
Okay, sir.
So in next class, I will define you the next part. Okay.
Thank you, sir.
Thank you.